హలో చెప్పమ్మా. అయితే రమా మేడంతో మాట్లాడండి ఒకసారి. Students, in the last class we have discussed about prime spectrum and all. So today we will do stone duality between Boolean rings and Boolean spaces. A ring R is a ring R is said to be a Boolean ring if A square equal to A for every A belongs to R. Okay, so here what are the major properties of Boolean rings? In a Boolean ring, we have A plus A is 0 and A plus B equal to 0 implies A equal to B and AB is equal to BA. That means a Boolean ring is always a commutative ring. Now, let capital B, next theorem, let capital B be any Boolean space Boolean capital B be any Boolean ring. Then B be the prime spectrum of P. Prime spectrum of P. Then spectrum of B is a Boolean space. Spectrum of B is a Boolean space. See how we prove this. Suppose we have already proved that we know that proof. We already know that spectrum of any ring is, that is the prime spectrum. Prime spectrum of any ring is always a compact space. It is always a compact space. Okay, so for any A belongs to B, now we prove that spectrum of B is a Boolean space. For this, what we will do, we define an open set XA such that the set of all P belongs to spectrum of B such that A does not belong to P. Okay, that means you have A into, we know that A into 1 minus A, because B is any Boolean ring, we have A into 1 minus A is 0 and A plus 1 minus A is 1. So it can be seen that for any prime ideal P of B, we have A belongs to P if and only if 1 minus A does not belong to P. So you have what is the spectrum of P minus x of A. This is nothing but x of 1 minus A. So what do you mean by that? This is x of A is closed. X of A, because x of 1 minus A is open, you have x of A is closed in spectrum of B for all A belongs to B. Therefore, you have the set of all XA such that A belongs to B is a base for spectrum of B consisting of closed sets, or you can set closed and open sets, that is open sets. Also, if P does not be not equal to Q belongs to spectrum of B, then P is not a subset of Q or Q is not a subset of P. Therefore, if A belongs to P minus Q, then X into 1 minus A and XA are disjoint open sets containing P and Q respectively. Therefore, what do you mean by that? This is spectrum of B is a Hausdorff space, and hence it is a Boolean space. And this is one important theorem. And the next one, next theorem is the maximal spectrum of any ring is compact. The maximal spectrum of any ring is compact. Let R be a ring to prove this. Let capital R be a ring and Y is equal to maximum spectrum of R. Now we say that Y is compact. Okay, why we say that Y? When we say that Y is compact, every open cover has a finite subcover. Okay, that means in commutative algebra in this unit, we are trying to correlate the relationship. We are trying to have relationship between a topology and these spaces, Boolean algebra, rings and topological spaces. Okay, let R be a ring and Y is maximum spectrum of R. So see here, you know that the set YA is equal to the set of all M belongs to Y. M is the maximal ideal such that A does not belong to M, but A belongs to R, form a base for the topology, on Y. Okay, so if we prove that every open cover of Y consisting of basic open sets has a finite subcover. To prove that Y is compact, it is sufficient. It is sufficient if we prove every open cover of Y consisting of basic open sets. Basic open sets has a finite subcover. It has every basic subcover. What you call every open cover has a finite subcover. Okay. Now what is the open cover, Amma? Just now we assumed that Y of A such that A belongs to A. Such that A belongs to A. Be such open cover of Y where A is subset of R. Where A is a subset of R. Then if you take Y is equal to union of YA, where A is sub and Y is the union of A belongs to A, YA. Let I be the ideal generated by capital A in R. Let I be the ideal generated by capital A in R. If I is a proper ideal, we know that every maximal ideal contains all other ideals. Okay. If I is a proper ideal, if capital I is a proper ideal of R, then capital I is contained in a maximal ideal capital M of R, and we get capital M belongs to capital Y and A is the subset of I is the subset of M. That means M does not belong to YA. So for A belongs to A. So this is a contradiction. Therefore, I is not a proper ideal. Because M is maximal ideal, you have I is equal to R. When I is equal to R, I generated by M, no, I can be written as R1A1 plus R2A2 plus so on RNAN for some AI belongs to A. Okay, and Ri belongs to R. And Ri belongs to. So what do you mean by that? Since every maximal ideal is a proper ideal, because every maximal ideal is a proper ideal, it should not contain at least one AI. So from this you will get Y is equal to union I is equal to 1 to N. It follows that capital Y is equal to union I is equal to 1 to N Y of AI. That means it is a finite subcover. Hence, Y is compact. So this is one important theorem. The maximal spectrum of any ring is compact. Okay. Next one. After this, you go for section 7 or unit 7. Now we have finitely generated modules. Unit 7. Finitely generated modules. What do you mean by finitely generated modules? We know what is a module. Let M be a module over a ring R. Let capital M be a module over a ring R. Okay, we say that capital M is finitely generated. Finitely generated if there is a finite subset capital X of M such that every element of M is of the form A1x1 plus A2x2 so on plus ANxN for some xi belongs to X and AI belongs to R. And we say that capital X generates M. Everyone should focus only on the definitions. If you know definition very well, we will be able to prove the theorem. What do you mean by a module is said to be finitely generated if it can be expressed as linear combination of elements of capital X and R. So here, see, a finite subset X of M such that every element of M is of the form A1x1 plus A2x2 so on ANxN. All of us know that this is a linear combination of elements. So we say that M is finitely generated or X generates M. Capital X generates M. Here, one important theorem is if capital M1, M2, etc., Mn be modules over a ring R, and capital M is equal to M1, M2, direct sum of so on Mn, then and M, this is the direct sum of Mi. Then capital M is finitely generated if and only if each Mi is finitely generated. Okay, this is one important theorem. How you prove this? Suppose, see, each Mi is finitely generated means you can write what is the direct sum of Mi's? Direct sum of Mi's means you can write x1 plus x2 plus and so on plus xn. Each element of M. Suppose if x belongs to M, then x can be expressed as uniquely expressed as x1 plus x2 plus and so on plus xn. Okay. So suppose each mi is finitely generated. If each mi is finitely generated means you will get some a1 x1 plus a2 x2 plus and so on plus an xn. So each mi, this belongs to mi. So, but mi is the direct sum of m. So, whenever each mi is finitely generated, your m is also finitely generated. Conversely, suppose m is finitely generated. What do you mean by capital M is finitely generated? If capital M is finitely generated, then there exists a set capital Y such that Y1, Y2, etc. YR of elements of M which generates M. These are all elements generates M. So what do you mean by that? That means generating finitely generated means you will get yi is equal to sigma j is equal to 1 to n xij, where here you have xi1, xi2, so on, xin. Okay, generates mj. So your x can be written as, tell me, if generates mj means you can write your x as sigma I is equal to 1 to some r ai yr, or this is sigma I is equal to 1 to r ai. What is yrm? Yrm is sigma j is equal to 1 to n xij. yj పెట్టుకోండి, yj. This is nothing but sigma j is equal to 1 to n, sigma I is equal to 1 to r aij xij. So what do you mean? That ai, because don't take another constant, ai into xij. So this is that is x is also the linear combination of xi1, xi2, etc. xin. That means what do you mean? Each mj naught or each mj is finitely generated. So whenever each mi is finitely generated, then m is finitely generated, and whenever m is finitely generated, each mi also finitely generated. Okay, this is one important theorem from this section. Now, students, now I want to discuss about, all of you know about homomorphisms and isomorphisms. See here, just let us recall the concept of a homomorphism. We say that suppose F is a mapping from a ring R to R dash. Then we say that F is a homomorphism if F preserves the binary operation. F preserves the binary operations. That means we have f of a plus b is equal to f of a plus f of b, and f of ab is equal to f of a into f of. Now we call a 1-1 homomorphism is called a monomorphism, and onto homomorphism is called epimorphism. A 1-1 and onto homomorphism is called an isomorphism. So today we will prove by making use of concepts of this homomorphism and isomorphism. We will prove 9 lemma and 5 lemma. Okay. See here, students, just students, next go to this section 8.3, exact sequences. One of the important tools used in the study of commutative algebra is concept of this exact sequences. See here, a sequence of R modules, a sequence of focus mainly on definitions, a sequence of R modules and R homomorphisms allows them you get, this is in increasing order, M1 to M2 to M3 up to like that. Mn minus 1 to mn plus 1 is said to be exact if image of fn minus 1 is kernel of fn. If this is exact at each mn, then we say that it is an exact sequence. See here, but before that, see, whenever there exists a homomorphism, we can have kernel of a homomorphism. What is the kernel of homomorphism? The set of all those elements of R which are mapped onto identity element of R dash. Kernel means you have kernel of f is the set of all x belongs to R such that f of x equal to 0 you can take, or 0 dash means 0 is the 0 element of ring R and 0 dash is the 0 element of ring R dash. And we know that kernel of f is an ideal. Kernel of f is an ideal. Now here, just in the above, the exactness at Mn is equivalent to say that x belongs to Mn, Fnx equal to 0. That's what I'm saying. Here, image of Fn minus 1 is kernel of Fn. What is the kernel of f? Kernel is the set of all those elements which are mapped onto 0 element of ring R dash. Okay. In this sequel, you can write 0 tends to M or M tends to 0. Both are similar. See here. That means a sequence f from M to N is exact if and only if f is a monomorphism. Monomorphism means, I told you, a 1-1 homomorphism is called a monomorphism. Onto homomorphism is called epimorphism. Okay, is exact if and only if f is an epimorphism. And also the mapping 0 to m dash to m to m double dash, it tends to 0 is exact if and only if f is a monomorphism. That means you have, see here, f is a mapping from, here you have f is from m dash to m, g is from m to m double dash. So you have kernel of g, image of f should be kernel of g, and g is epimorphism. So in this case, f induces an isomorphism. Okay. Now, after this, all of you know what is the fundamental theorem of homomorphism? Fundamental theorem of homomorphism is states that every homomorphic image is isomorphic to some quotient ring. That is, every homomorphic image of ring R is isomorphic to some quotient ring. That is some R by S, where S is an ideal of R. Okay. See here, look at this theorem. Suppose that the following diagram of R modules and homomorphism. Focus on this diagram. F is a mapping from M to N. G is a mapping from N to N. Then here alpha is a mapping from M to M dash. Beta is a mapping from N to N dash. And gamma is a mapping from N to P dash. Okay. Just to go through this diagram, what is mean by F, G, F dash, G dash, alpha, beta, gamma. Alpha, beta, gamma. See here, exact rows chudandi. So what you have to take, see, if alpha, mapping, look at this mapping. M is from, F is from M to N. G is from N to N. Alpha is from M to M dash. Beta is from N to N dash. Gamma is from N to P dash. Okay. So what he says, then the following are true. Because to prove 5 lemma and 9 lemma, this theorem is very important. Just to see, if alpha, gamma, G, ante entama, here alpha is from M to M dash. Gamma is from N to P dash. G is from N to N. Then what he says, these are all epimorphisms. Then beta is also epimorphism. Beta is also epimorphism. Again, if alpha, gamma, F dash are monomorphisms, then you have beta is also a monomorphism. If beta is epimorphism and F dash and gamma are monomorphisms, then alpha is epimorphism. If beta is a monomorphism and alpha and G are epimorphisms, then gamma is a monomorphism. Students, try to understand this concept. Even though this is a little bit difficult, just to go through. If you have an idea of this picture, then definitely it is easy for you to prove other theorems. Read the theorem. Here, we have alpha, gamma, G. Okay, alpha, gamma, G. If they are epimorphism, epimorphism means onto homomorphism is called epimorphism. Similarly, alpha, gamma, F dash. They are monomorphisms, then it is beta is also a monomorphism. Again, if beta is an epimorphism and F dash and gamma are monomorphisms, then alpha is a epimorphism. Like that, you prove this. Okay, this proof is one important theorem. This is one. And based on this, you have to prove the 5 lemma. Suppose that the following diagram of modules and homomorphisms is commutative and has this. Okay, then the following holds. If alpha is epimorphism, beta and gamma are monomorphism and gamma is a monomorphism. If eta is a monomorphism, this symbol is eta. Beta, gamma are epimorphisms, then gamma is epimorphism. So if alpha, beta, delta and eta are isomorphisms, then gamma is also a isomorphism. So just look at this diagram. This is known as 5 lemma. See here. 5 alpha, beta, gamma, delta, eta. First, see here. Before reading this theorem or before learning this theorem, you should know what is an epimorphism, what is a monomorphism. Okay, and what is a monomorphism and what is an isomorphism. Epimorphism means onto homomorphism. Monomorphism means 1-1 homomorphism. Isomorphism means a 1-1 onto homomorphism is called an isomorphism. See here. First one, suppose alpha is epimorphism Chudinamma, if alpha is epimorphism, beta and gamma are monomorphisms, then we have to prove that gamma is monomorphism. Ante enti, you have to prove that gamma is a monomorphism means let C belongs to C such that gamma C is 0, then delta into H of C is nothing but H dash of gamma C, because delta H is, see here, gamma C is 0, then delta H of C is H dash of gamma C, which is 0. That is HC 0 means you will get C belongs to kernel of H. C belongs to kernel of H means, student, kernel of H means, C belongs to kernel of H means it is exact sequence, no? It is equal to image of G. Kernel of H is equal to image of G. Because C is the kernel image of G, for some B belongs to B, you have C is equal to G of B. Okay? Take G dash on both sides, G dash beta B, which is equal to gamma into G of B, which is gamma C is 0. Or beta of B is equal to kernel of G dash. Kernel of G dash is nothing but image of F dash. This follows from exactness of the sequences. Beta of B is F dash of A dash. For some A dash belongs to capital A dash, or A dash is equal to alpha A for some A belongs to A. Why? Because alpha is an epimorphism. Just to go through this diagram. Okay, here what you will get, beta of B is equal to F dash of A dash, which is equal to F dash of alpha A. A dash means alpha A. Alpha A. F dash of alpha of A, which is beta of F of A, which is implies B equal to F of A. Why? Because beta is 1, 1 and beta is 1, 1 and when do you say that a function is 1, 1? If distinct elements has distinct images, that means you got finally beta of B is equal to beta of B equal to beta of F of A. So because beta is 1, 1, you get B is equal to F of A. What is B and A? This is C equal to G of B, which is equal to G of F of A, which is 0. So what do you mean by that? Gamma is a monomorphism. Okay. See, students, more focus on this 5 lemma. Try to understand this concept before learning theorem. See here, what you will write first. Here you have try to understand these given concepts. F is from A to B. G is from B to C. Then G circle F is from A to C. Again, H is from C to D. I is from D to E. So 5 sets he has taken. So that is the reason it is called 5 lemma. Okay. Now you have, see here, alpha is from A to A dash, beta is from B to B dash, gamma is from C to C dash, delta is from D to D dash, eta is from E to E dash. Given that these are all epimorphisms and monomorphisms. Next one is 9 lemma. Next theorem is 9 lemma. Suppose that the following diagram of modules and homomorphisms is commutative and has exact rows, and suppose that middle column is also exact. Exact means, when do you say that sequence M2 M dash, that the 0 tends to M2 M dash is exact if image of, if you take F, image of F is kernel of F dash. That is the reason we call that, that's what you mean by exactness. Now look at this 9 lemma. So these two are the important theorems from this homomorphisms, 5 lemma and 9 lemma. So what he says, suppose that the following diagram of modules and homomorphisms is commutative and has exact rows. And suppose that middle column is also exact. If this is exact and this is exact, then what he says, this is also exact. When do you say that this row is exact? And if image of G dash is kernel of F dash, image of G is kernel of F. So you have to prove that image of G double dash is equal to kernel of F double dash. This is what you have to prove. Always based on, focus on two things. What is given and what you have to prove. So what we will prove? Image of, we prove that image of gamma dash is equal to kernel of gamma. I think okay, based on the definitions of functions, you have to prove. Suppose the first column is exact. Okay, given that first column is exact. What do you mean by first column is exact? See here. This is the third column. Third column is exact. This is what we have to prove.